Hey, so I want to redo 1.41, so problem 1 from 7.4, and at least want to work at that same initial value problem, y prime is equal to, look up t divided by y, where y of 0 is equal to 1. And this time I want to do it with the second order RungeKutta method to see how they compare. So what's really important here for these tables is I still like to have what step I'm on. So 1, 2, 3, say. I like to have the t values, the y values, my function value, so the function value at tn, yn. But what's going to be exceptional here for my new equations is that, well, I'm going to also want a few more values in my table. So my table might be kind of large. Kind of wish I didn't use red. It's kind of, I feel like I'm a Sith Lord suddenly. Because we're going to be in this method sort of sending scouts out and looking ahead half a step, I'm also going to include t n plus h over 2. I'm going to include, well, you maybe recall from the method that the y value halfway ahead be yn plus h over 2, and what they called for us k and 1. What's important to recognize is that this right here is k and 1. So whatever value is right there is really what we're referencing in this new section. Oh man, I'm going to totally run out of room here. And the last value in my table is going to be my function value that sort of shows up halfway along. So that's given by, often called k, then 2, which is really the function value at the point from the 2 prior to this. And so we'll sort of see how we can get a nice bit of a cycle. So let's see what we do. So start out with our initial value. So t is 0, y is 1. And what we need to be given here is a step size. So let's say h 0.1. Now for the function value, it is just plugging in right before to this right here. So we end up with 0 divided by 1, so that's 0. And let's go ahead and keep it the same color for this first row. That's 0 right there. Now for my t of n plus h over 2, this is my scouting mission. So if you recall, something that maybe we spoke of a little bit is this method, sort of an idea behind this method is instead of acting like we would in the Euler method, so if we had sort of a graph here, instead of saying, okay, well, we're starting at the first point, let's just go all the way out there to the next point and see what the slope's over there. We're going to go out halfway and sort of reassess what slope we should have been traveling at this whole time. We send back that information, and whatever that new slope halfway along is, that's what we have the actual team go along. So if the slope halfway through is a little bit steeper, it would say we should have gone according to this blue line, so let's just go according to that blue line. So what we need to do then is find this point halfway through and see what's the slope over there to inform where we do our actual motion forward for our first and second column in this table. So let's sort of zoom back in then. So with a step size of 0.1, that makes this next value right here 0.05. For this next column, I think, well, where am I? So y is currently 1. We're adding to that 0.05 times the k value from before, which, just to code a coordinate, that was 0. So this is, the whole thing is equal to, maybe we'll do it in yellow. It's equal to 1. So that's that first value there. So there's 1. And then to find my new function value here, that is my t value that's looking halfway ahead over my y value looking halfway ahead. So it's 0.05. So this is really the slope that we would have come across if we looked ahead. So that's the slope we're going to use. So coming back to the first column, we think, well, as we go forward according to our step size of h, my new y value will be, well, where I am right now. So you can do sort of some side work. So my next y value, so y of 1, I am writing behind that little webcam image. And so let's just go ahead and move that webcam image over here. So my new value here is where I am. And we're going to add to that the slope, the best guess of a good slope. And so that is my kn2 value. So for this one, it's going to be 0.05. I'm sorry, we're going to do the step size of 0.1 times that k value, 0.05. And our current y value, y of naught, right here is actually just 1. So that's what we're going to use. We're going to use 1. So this gives you my new y value is 1 plus 0.005. So 1.005. So that's the whole process, and then we just keep doing this sort of over and over. So my next function value here, right, is your y value 0.1 divided by 1.005. So that gives you about, I'll write it approximate here. No, how about this? Let's just write it in the fraction form for now. I like that because that, for a little while, at least before that gets too gnarly, keeps it exact. So if we look halfway ahead from the point that we're at, well, we are currently at t being 0.1. So we look halfway ahead, so we get 0.15. Because we keep adding half of this h value. So where's the scouting mission at? Well, the scouting mission has gone forward half a step. It was just a moment ago at 1.005, and it's gone forward half a step, so 0.5, in the direction given by this function right here. And so 0.1 over 1.005. Now that whole thing right there is actually equal to, allow me to plug that into my calculator, so you can sort of see why it'd be a good idea to have some generous space for this. Like, I would not be, and also quick typo, there needs to be a 0.05 because we're going halfway there, plus 0.05 times, and then I actually have the value of that slope right there still saved in my calculator from the last entry, so I'm going to just use that and say this gives me an answer of about 1.009975, whatever. Okay, so I'm sort of putting a bunch of numbers in there. That's for my calculator, but I have that saved. So what would be the slope that we really should have gotten at? So we're going to use the location of our scouting mission at this t value and this y value and say, well, what slope is it where that scouting mission is at? Well, that scouting mission says the slope is your t value divided by your y value. So I'm going to do our t value is 0.15, and the scouting mission sends back 0.5 divided by that last number I had in my calculator. It says, hey, out here the slope is not this exactly. It's not what it was before, but out here the slope is actually closer to 0.1485, etc. So we say, oh, great, thanks for that information. We're going to use that. So when we go out to the t value of 0.2, instead of going according to this slope here, we are going to use the slope that the scouting mission has discovered for us, the slope given over here by this value, which I currently have saved in my calculator. So to do that, I'm going to say my next y value is, well, where we are, 1.005. we're going to add to that the h value times the slope there. So k, and here this is my 1, 2. Okay. So this being k, so 1, 2. Now allow me to plug that into my trusty calculator here. So 1.005 plus 0.1 times the value I have saved in my calculator. And I get for this value here of 1.01985. I have a cat beneath my feet, perhaps you hear it. Great, so let's actually just compare this real quick to the method that we had before. So before, when we went along this, at this point we ended up with either 1.0149, that was one of our values. We also had 1.0298, and we saw in those last videos, sort of scrolling down, excuse me, that the exact value is 1.0198. Well, where are we now? Well, we just found 1.0198. Look how close that is. 1.019804 is exact. Our value for t being 0.2 is 1.01985. So this is clearly at that point much more accurate than the other methods. This is normally the case, not always, but normally that is what happens. All right, great. I hope this was helpful. Just buckle down when you need to get into these higher order numerical approximations. There's a reason, I'm just going to put this out there, that we use calculators, and there's a reason we use computers, because this process, which is rather laborious by hand, is not intended to be done by hand, really. If we were in the age pre-computers, yes, that's what you would have to do. So Euler's method, he would have thought about this, and you could actually get very accurate things. But for us nowadays, these are really computer methods with these numerical analyses. The reason we do it by hand is to recognize that we know how it works, that we could do it by hand. Because if you can't do it by hand, at least in the concept of the structure, then it's likely you're not quite familiar, or as familiar as you could be, with the workings. So it actually is much easier to code or put into a computer once you know this process. All right, great.